Hi there. This video is on Chapter 9, Sections 9.1 through 9.3. And just to recap a little bit, previously we have been looking at a sample to try to say something about a population. For example, we want to find the average height of 10-year-old girls. It's almost impossible to find every 10-year-old girl and measure their height. So we take a sample of 10-year-old girls and we find the average height of that sample. And we use that to estimate the average height of the population of all 10-year-old girls. Or perhaps we're trying to figure out people's opinion on a particular issue, whether they're in favor or against it. Very difficult to find everyone in the population and ask them the question. So we take a sample, and based on the people who say yes or no in that sample, we're going to try to make a prediction about the total population. So that's a big idea in statistics. And we're going to continue that big idea. But in this chapter, we're comparing two populations. So we have three specific learning objectives in comparing two populations. The first one here is comparing two independent population proportions. So independent means that, like, knowing something about one population or some fact about a particular population does not impact the other population. And we're looking at proportions, how many people feel this way, or, how many heads or tails were flipped that way. So it's independent population proportions. The second learning objective, again, we're looking at independent populations, but now we're trying to calculate their means. So the mean of one population compared to the mean of the other population. And lastly, we're going to be looking at two dependent populations. So now one definitely, relates or impacts the other. And we're going to be, again, looking at the averages. And the way these are paired, or the way these are dependent, is specific. They're paired up in some way, right? So instead of just like a bunch of women and a bunch of daughters, we have a pairing of a woman and her daughter, right? So those are paired up instead of just the general population of one and the general population another. Every item in one population is paired with another item in the other population. Or for example, suppose we time how fast you can run, and then we give you some sort of training regimen, and then we time again how fast you can run. So we're pairing your before running time and your after running time. We don't just look at all the people and their befores and all the people and their afters, but we're literally pairing up your specific pair of before and after and my specific pair of before, after, etc. So we're pairing up all the pieces of data. All right, so let me go into some, statistics language and formulas and do some examples so you can see how this stuff works in chapter 9. Okay, so the first learning objective was the independent population proportions. So we're going to be looking at two populations and comparing the proportions of those two things. So population one, population two. That means we need to take a sample from each of the populations. So we have some symbols over here where we have n with a little like number one kind of down below. It's called a subscript. And so the ones refer to population one and the twos refer to population two. So we have the sample size and the number of successes, the sample proportion, and fail sample proportion, success sample proportion, and fail sample proportion. And those use similar symbols as you've seen before, but they also have the little numbers next to them. So we can distinguish one population from another. We also have this kind of newer calculation that you may not have seen before called pooled proportions. So this is like the total number of successes divided by the total sample sizes combined together from the two samples. So you take all the successes from both populations, add them together, take all the sample sizes from the two populations, add them together, and that will be the proportion of the both samples. The pooled proportion is what the math people call it. And if that's a success pooled proportion, then we have a failure pooled proportion, which is just the other part of the 100%. So 60% pooled proportion of successes means 40% pooled proportion of failures. Of course, we have all our lovely complicated statistics formulas like the Z-stat, the margin of error, things like that. People who want to do these formulas by hand, you're welcome to do so. It's really nice to be able to use technology to do them because it's usually much faster and less prone to calculation mistakes. So we're going to be doing these calculations using StatCrunch, but I want to put them there in case you want to do them by hand or double check them, things like that. So there are some questions where it asks you, like, what would the sample size be? And so there's a formula for calculating the sample size. Again, it's on StatCrunch, or you can do it by hand. So those are the formulas for the two population proportion comparisons. One more thing I'll remind you about, which is very, very small. One more thing I'll remind you about is that for confidence intervals, if we're doing a one-sided test, our confidence level is 1 minus twice the significance level, 1 minus 2 alpha. But if we're using a two-sided test, it's just 1 minus alpha. All right, we'll see that in some examples as we go forward. Okay, so my first example here, it says, I'm interested in whether or not Republican voters are more religious than Democrat voters. A simple, so what I do is I need to collect some data, some sample data. So what I have here is, this is fictitious, but suppose I collected a simple random sample of 2,100 registered Republicans, and I asked them how many of them report attending religious services at least once a month, and I got 1,295 registered Republicans out of 2,100 people surveyed who say that, yeah, they attend religious services at least once a month. And I do the same thing with registered Democrats. I get 2,300 registered Democrats, and I find that 1,002 of them report attending religious services at least once a month. So now I'm going to analyze the populations based on these two samples. And we're going to do it 2 ways. We're going to use a hypothesis test, and we're going to use a confidence interval. So just to be clear, a hypothesis test tests a claim, whereas a confidence interval is used to estimate something about the population. In this case, we're going to be estimating how close the two population proportions are. So first, we're going to test the claim. The claim is, well, it's up here. It says, are Republican voters more religious than Democrat voters, right? So there's this idea that we have more these Republican voters than Democratic voters with a certain characteristic. So for our hypothesis test, we're going to have an HO and an H1. HO is always an equality statement. So even though we're sort of testing a claim with a more word in there, the null hypothesis is always equal. So we're going to say that basically the equality is they're the same. So we would say that the proportion of the first proportion of the population proportion of the Republicans is the same as the population proportion for the Democrats. And then an alternative would be that the first population, the Republicans, are greater than the second population, which is the Democrats. So those would be our null and alternative hypotheses. By the way, depending on which spreadsheet program you use, they may not have P1 equal to P2. They may say that if P1 and P2 are supposed to be the same, which is the null hypothesis, that means that P1 minus P2 is equal to 0, right? If they're the same, then we subtract them, you get 0. And if P1 is bigger than P2, when you subtract them, you still get the greater than sign, but it's 0 now. So in fact, you'll see this on StatCrunch that they oftentimes will use not the equals directly, but they'll say it's equal to 0 or greater than 0 with a subtraction. And this kind of mimics what we're doing, because in order to do a comparison of populations, I think I skipped this up here. What we're going to do is, I skipped it on the first page. So let me go back real quick and read it. So the part I skipped, sorry about that, was we're going to analyze the differences between the two proportions. We're going to look at a sample from each, and we're going to find the proportion from each sample and subtract to find the differences. How different are these two proportions? That's the basic idea for doing this. And in order to have all these formulas like be correct, actually give accurate predictions, we require that each population sample be a simple random sample and be independent. And the number of successes and the number of failures for each sample is at least 5. So back to page 2. So do we have SRS, independent SRS? Yes, we have a SRS for both the population 1 and the population 2. And asking a registered Republican does not influence whether I ask a registered Democrat. In other words, the registered Democrat won't change their opinion just because I asked some registered Republican that they have no knowledge about, right? So I'm not influencing one. They have no dependence relationship. And each of the successes are 1295 or 1002, and the failures are also bigger than 5, whatever the remainder from the 2000 numbers. So we satisfy all the requirements for our formulas. And now we're going to try to do a hypothesis test at the significance level of 5%. So that's the setup for the situation. And we're going to be using our StatCrunch to go ahead and do so. Significance level of 5%. So I'm going to head over to StatCrunch. I've actually typed a bunch of the stuff in here. I'll show you how to do it straight away. You're going to go to the stat pull-down menu, and you'll see that there's something called proportion stats. And we've been doing this actually in the previous chapters. Instead of doing one sample, we have 2 samples. So we're going to do 2 samples. And we don't actually have the raw data. We have summaries. So I'll do 2 sample with summary, and it asks me to fill in the number of successes and the number of observations for the first population, those are registered Republicans, and I do the fill in the set for the second observations, and then I set up my hypothesis testing. Like I said, I actually did this already, so just to save me time typing in all the stuff. So I'm going to go to my 2 sample proportion, and I'll just edit this thing. And so I'm going to be doing a hypothesis test. Here's all the numbers that I typed in. We have P1 minus P2 is equal to 0. That was our null hypothesis. And P1 minus P2 is greater than 0. So we had a greater than for our alternative hypothesis. And then we're going to hit compute. And this is the readout for our hypothesis test. It gives us a bunch of information, numbers and stuff. I personally want to focus on the p-value, which is less than 0.0001. Basically, it's 0 if you round it to 3 or 4 decimal places. I guess 2 or 3 decimal places, it's 0. 4 decimal places, it rounds to, well, something like 0.0001. Okay, so I know the p-value is basically 0, and I'm gonna, in doing your homework, you want to put the, you want to copy and paste the StatCrunch readout. So that's what you put here, and then you put the p-value is equal to basically 0, and then you would say the p-value of 0 is less than the significance level of 0.05. 0.05. So if the p-value is super small, it's lower than the alpha value, then we know that the probability of these samples being collected and the null hypothesis still being true is really improbable, right? Almost no probability that we could possibly get both or have both equal proportions in the population, but get samples with such different proportions. So we conclude, therefore, we reject the null hypothesis. So what does that mean for us? So if we reject the null hypothesis, that tells me that we now have enough evidence to support the fact that there are more Republican voters than Democrat voters who at least attend religious services at least once a month. I don't know if we can generally say that means they're more religious, but definitely in terms of reporting that they attended religious services once a month, we know that that the hypothesis test there supports that. So we could also say here or more specifically, we have enough evidence to say that there are more registered Republicans who attend religious services at least once a month than registered Democrats do. That doesn't look like an S. Democrats do. Okay, so we have enough evidence to reject the null hypothesis in favor of the alternative hypothesis, which says that we think that the proportion, the first population proportion is greater than the second population proportion. All right, so let's do the same kind of analysis, but using a confidence interval. So I'm going to go back to StatCrunch. Remember, the significance level is 5%. That's how we compared the p-value of 0 to the alpha value of 5%. So I'm going to go back over here. I'm going to go to edit. And instead of doing a hypothesis test, I'm going to do a confidence interval. Now, notice I put in 0.90, and that's because we're doing a confidence interval, but it's only a one-sided test. So we have to double the alpha. So 5% double is 10%. And so 1 minus 10% or 100% minus 10% is 90%. So that's what you have to do for a one-sided test. Confidence level, excuse me. When you have a one-sided relationship, you have to double the alpha to find the confidence level. All right, so then I'll do compute, and it gives me the readout for the confidence interval. And again, I would just sort of copy and paste this to my homework or my test or whatever. But the lower limit, upper limit, these numbers right here are the ones that are especially relevant. This is 0.15. I'm just going to round this to 2 decimal places, so 0.16. And this is about 0.21. So my confidence interval is between 0.16 and 0.21 when I round those to 2 decimal places. So, I put my little readout here, I put my readout. That's supposed to say readout. Readout there, and then I have a lower limit. I think that was 16% if I remember, and an upper limit, I believe it was 21%. So we have now 90% confidence. So we are 90% confident that the actual difference in proportions, and this is between the registered Republicans and registered Democrats. So we're 90% confident that the actual difference in proportions between these two populations is between, well, these two numbers, between 16% and 21%. So that kind of backs up the findings we had from the hypothesis test, because we're 90% confident that there's between 16% and 20% more Republicans than Democrats, and that's pretty strong evidence that they're not the same, right? We're pretty confident that it's like not even close to the same, 16 to 21% more than one population more than the other. All right, so that's an example of doing both a confidence interval and hypothesis test when we're comparing the proportions between two populations. Let's do a similar thing, but with the means over here. Okay, so here's my mean page. So for this one, just to remind you, we're comparing two independent population means, and we're going to be doing it both using a hypothesis test and confidence interval. All right. So once again, we're going to be analyzing the difference between the two populations. In this case, we're going to be analyzing the difference between the means of one sample and another sample. We're going to analyze the difference between the mean of sample from population one and the mean of the sample from population two. In order for all our formulas and statistics to actually have accurate results, we need a independent simple random sample for each of those samples, and we need the sample size for each sample to be at least as big as 30 or bigger than 30. So those are like the requirements you had for any kind of t-test. You need sample size to be bigger than 30 for the formulas to work out. Okay, so symbols. Again, we have the ones and twos for population one, population two. N1 is the sample size for population one. X1 with a bar would be it's a bar on top. I had to write it in myself there. That's the sample mean from the first population, and S1 would be the sample standard deviation, and we get the twos for the same for population two. We also have the degrees of freedom. You may remember that from before using t-tests. And we just had the degrees of freedom always being one smaller than the sample size. We have two different sample sizes here. We have N1 and 2. So for the degrees of freedom, you just take the smaller of the two. So you look at N-1 minus 1, N2 minus 1, and you take the smaller of those two. There are some complicated formulas to get a better, more accurate measurement of degrees of freedom. But we're not going to do those formulas, are very complicated. So if you're going to be asked for degrees of freedom, just take the smaller of the N1 minus 1 and N2 minus 1. And we have our t-statistic formula and our margin of error formula, which again, we're going to be using StatCrunch to do the calculations instead. Let's look at an example so I can show you how this works. All right, so here's my example for this one. The English Premier League, if you haven't heard of that, it is the highest level of European football, oftentimes called soccer in this country. The National Football League is also the highest level of American football. And this question is for this particular example, the question is, are the average player salaries about the same for the two leagues? So that's what I'm trying to find, are the averages for these two high level sports leagues about the same. So I went to the internet and I grabbed a bunch of data. So I went to this particular website that I have here, the URL, and I took a SRS, a simple random sample of 67 European football players, and found that their average salary was about 4.25 billion and a calculated standard deviation of about 3.9 million. So I got some information from that website. I took about 10% of the players to make my sample. And I went to a similar website to find the salaries of NFL players. And for there were a lot more players in the NFL than there in the Premier League. So I took 256 American football players, as about 10% of them, and found that the average salary was about 3.3 million with the standard deviation. I calculated all that stuff from the website. Okay, so now we're going to analyze this like we did the last one. We're going to do a hypothesis test. So for our hypothesis test, we need a null hypothesis and we need an alternative hypothesis. So our null hypothesis will always be equality. So we want that well, in this case, we're doing the mean of one population compared to the mean of another population. So we'll call it mu is that symbol we use for population mean. So we'll say mu sub 1 equal to mu sub 2. In other words, the mean salary for the Premier League players is about the same or equal to the mean salary for the NFL players. And remember that we are probably going to write this as mu1 minus mu2 is equal to 0. because we're using StatCrunch. If you're using Excel, you might have to do it mu1 equal to mu2, but depending on what program you use, it'll be one of these two. And then for alternative hypothesis, well, if we read this statement, it just says, are they about the same? It didn't say, is one more than the other? It says, are they the same? So the alternative is they're not the same. So the alternative hypothesis would be that mu1 just is not equal to mu2. Or if you want to do the subtraction version, you would say mu1 minus mu2 is not equal to 0. The not equals version. And then we're going to do our StatCrunch and get the readout and stuff like that. So I'm going to go over here to StatCrunch. I'm going to hide this one here just to run through where it is again on StatCrunch under stat. The comparing means is either Z-stats or T-stats. We only use Z-stats if we know the population standard deviation, which there was no mention of a population standard deviation on the website. So I don't know how I could possibly use Z-stats because I don't know the sigma value, the population standard deviation. So in those situations, we use T-stats. So T-stats, and we have a 2 sample now instead of 1 sample. And again, we just have a summary of the data. We don't actually have the data. So I'll do a 2 sample with summary. And I get this little readout where it asks me about each of the populations. It asks me for the average for each of the populations and the standard deviation, the sample size, and all the stuff like that, and then hypothesis testing. As I said, I already put all the numbers in just to kind of make the video run a little bit more smoothly. So I'll go over here, 2 sample T summary right here. I need to edit it to go to hypothesis test. And the mu1, mu2 is equal to 0 versus mu1 minus mu2 is not equal to 0. So this is already set up for us. Here's all the numbers that I typed in, and I'll hit compute. And here's the readout for the hypothesis test. Once again, it gives a lot of information, but the p-value is what I'm really interested in. P-value is about 0.12. So, normally I would just do I would cut and paste my little readout here, right? Readout. And I would say my p-value was about 0.12. And so now I'm looking at a significance level of 5%. So the p-value of 0.12 is not less than 0.05, which is our alpha value. And some people may write this as the greater than thing, which is fine. Whichever way you want to write it, we know that the p-value is not low enough. The p-value has to be lower than the significance level for us to reject the null hypothesis. And this didn't happen. We had 12% versus 5%. So we do not reject the null hypothesis. So what we just basically say is, I'm going to write it up here somewhere. So we don't have enough data to support rejecting the fact that the Premier League players mean salary. So we don't have enough evidence to reject the fact that this is the word support. I can't even read my own handwriting. That's how bad it is. This says support here. We don't have enough evidence to support rejecting the fact that the Premier League players mean is the same as the NFL ones. The NFL players mean salary. All right, I squeezed it in over there. Sorry about all the messy board work here. Okay, so that's our hypothesis test and our conclusion. And now let's look at the same idea, but with a confidence interval. Let's scroll just a little bit more. Okay, there we go. So we're going to use the confidence interval to do the same thing. So I'm just going to go back over to StatCrunch, and I'm going to change this into a confidence interval. Just real quick, we're doing it at the same 5% level, right? Stimulus level of 5%, same again. So I'm going to go here, edit, and I'm going to switch this from hypothesis test to a confidence interval. Now I'm doing a two-sided test, right? It's a not equals 2. All right. So I just keep the alpha, the C minus alpha is 95%. I don't need to double it because it's not just looking at one versus the other. All right. So then I compute, and here we go. I got my lower limit, upper limit. So again, I'm going to cut and paste my printout. I have a lower limit of about negative 255,000, an upper limit of about 2.1 million. So that's the important information. 255, 2155. Okay, 255. Okay. So for my confidence interval, I have my little readout here, right? The info, and then I have lower limit of in fact, I didn't mention this, but I think it's negative 255,000, right? The reason why it's negative, it's over here. The reason why it's negative, look at it, it's negative, right? The lower limit is a negative number. That's because like that shows you that the first population has a lower mean than the second population, whereas the upper limit is a positive number, which would mean the first population has a higher mean than the second population, right? So, or even the sample too. So the lower limit was negative, the upper limit was positive. I'll put a dollar sign here. Positive 1 to I think it was like 155, something like that. I may not have the exact numbers, but it's pretty close to that, right? I'll put a little plus sign here, right? One's negative, one's positive, right? So now we know at the 95% confidence level that the actual difference between the average salary is between negative 255,000 and oh, this is actually not right. It's 2.1 million, right? That's why I have the one is wrong. It's 2.1 million, 2155. There we go. Sorry, I switched numbers in my head somehow. Okay. Nonetheless, I don't want to make people confused. Nonetheless, we have a range here from negatives to positives. So, like, it contains 0. And if you remember before, if your confidence interval contains 0, we don't really know which is higher, which is lower, because it's possible it's lower, it's possible it's higher, right? We don't really have enough information. I mean, it looks like there's perhaps more possibility that it's higher, but we don't have enough information to know one way or the other. So we are 95% confident that the actual difference in mean salaries, I guess mean player salaries, should I say? I don't know how specific I need to be. Mean player salaries between the Premier IER, I think, and NFL is between negative 255,000 and positive 2.155 million. And then we would say, because we can be smart about this. This interval contains 0, 0 is spelled with an R, 0, 0, 0. So we can't be confident that either population's mean salary is larger. All right, we just don't know whether it's larger or smaller. All right, so that's an example of doing a comparing two population means by using the sample means and then subtracting them. All right, we got one last learning objective and one last example. All right, so the last one we have here is we're comparing two dependent population means called matched pairs. We're again using hypothesis the confidence interval. Again, remember the way this works is we're going to be matching up each data item from the first population to one data item from the second population using some common characteristics. So everything from one population is matched to the other population. And again, we're going to look at how the differences are, right? We're going to be looking at how different the two are from population one and population two. In order for our formulas to actually give us answers that we can rely on, we need, again, independent simple random samples. And we also need either that the sample size of each sample is greater than 30, or that when we look at all these differences, the distribution of all those differences of those matched pairs is a normal distribution. So one of those two has to occur. So we'll do some symbols and then we'll do the example. So because they have to be matched up, the population sizes for each sample have to be the same. So we don't need an N1 and N2 anymore because we're pairing them up. We have to have the exact number of people in the first population sample as the second population sample so they can be paired up. We have this little D thing as our symbol right here to represent the differences between each pair. So D1 would be the difference between the mean values of the first pair. The D2 would be the difference between the mean values of the second pair, et cetera. And then D with a little bar on top would be the mean of the matched pair sample differences. And then we have our standard deviation and we have our population mean difference. Okay, so we are all the symbols there for us to be happy about. And then here's my example. My example here is my friend claims that year over year, the Oscar winner for Best Actress is generally younger in age than the Oscar winner for Best Actor. And so I went back to the interweb and I found the data for the winners in those two categories. And I put them into a StatCrunch spreadsheet. So here's the URLs I used in case you want to check them out yourself. And what I have here, let me just hide this here, is all the data, like the first actress to win. This is like Best Actress, Janet Gaynor for Seventh Heaven. She was born in 1906, and she got the award in 1929 when she was 22 years old. And then for the actor, it was Emil Jannings, and all the information there. Of course, the date of the award is the same, May 16th, 1929, because we're pairing these up, right? We're going to look at the same year and look at the actress and the actor at the same year and compare their ages. So one was 22, one was 44. And then for each of the years that the award was given out, we have the actress and actor. And this, all those for, I think, 70 or 75 years, whole bunch of years in the spreadsheet here. Okay, so 95 years, 93 years. Okay, so a lot of years of the award being given out. All right, so we're now going to be looking at comparing the ages for the women and the ages for the men, for the actresses and the actors. All right, and so we're going to be doing that at the 5% significance level. Okay, and again, we're going to be using hypothesis test and confidence interval. So the way I do this, I go under stat. I'm going to go under T-stats because once again, I don't know about the population standard deviation. And instead of doing one sample, we definitely don't have one sample. We have two samples. But instead of doing two sample, we're going to go to this last option, which is paired. So this is when we're pairing up one population with another. So I go to the paired thing and I say, where is the data from the first sample? And that would be not date of birth, but age when they won for the females, and age when they won for the males. That would be the two different things. And I would fill in, there's not much else to fill in, but like I said, I've done this before, so I'll just show you my prepared one here. And I think I need to change it back to a, yeah, hypothesis test. So age when one female, age when one male, hypothesis test. So we didn't write down the hypothesis test stuff. I have it here, but let's see if I did it correctly. All right, so for the hypothesis test, of course, we need an HO and an H alternative, or H1. HO is always going to be equality statement. So we're going to say that the mean age for the actresses is equal to the mean age for the actors, or of course, we just do the subtraction version of it as well. And then what does, well, we're testing my friend's claim, testing my friend's claim. So what does my friend claim? My friend claims that the Oscar winner for Best Actress is younger. So that means less than the age for the actor. So from alternative, I want the actresses to be younger or less in age, the average ages of the women to be less than the average age of the men. And in our subtraction version, it just looks the same thing with a less than sign like that. Okay, so now we know that the hypothesis test is equality and the alternative is a less than sign. So let's see if I did that right. I think I did, because I tested this out before. Yeah, here it is. The null hypothesis is that the difference, so mu d is the difference right here. Well, it says right up here, mu d is just the difference between mu1 and mu2. So the difference is 0. And the alternative is the difference mu1 minus mu2 is less than 0. And then I could do my computation. And there's my little readout. And it talks about a lot of stuff. And then I got the p-value here. P-value again is less than 0.0001, so it's basically 0. And that p-value being so low means I have enough evidence to reject the null hypothesis. So of course, I would put my info here, and my p-value is less than 0.0001. And so then I could make my conclusion, right? So so I know that, let me do that in red. So we have, just make this more space over here. So we have enough evidence to reject the claim that, well, the claim was, the null hypothesis claim was that they're equal, that the Oscar Oscar winning actresses are the same age. Okay, so I guess I actually put the word mean in there, that the Oscar winning actresses, oh, I didn't even put what we're measuring. There we go. The Oscar winning actresses mean age, there we go, that's where the mean goes, is the same or is equal to the Oscar winning actors mean age. And we think now we have evidence in favor of the alternative hypothesis. The alternative hypothesis was that the actresses is less than the actors. So we have enough evidence to reject the claim that the Oscar winning actresses mean age is equal to the Oscar winning actors mean age, in favor of the actresses being younger. So not just different, but actually being younger than the actors. All right, so that's the gist of the hypothesis test for this matched pair to population comparison. Okay, so let's just quickly do the confidence interval to finish this up. So if I go back to here, again, we're at the 5% significance level, but we have a one-sided situation. We're only doing one side of this. So confidence interval is always a plus or minus margin of error. So always got two sides to a confidence interval, no matter what we do. So I have to double the alpha value when looking at the C-value. So if I take off hypothesis test and do confidence interval, notice I'm back to 90% because of 5% significance level. If I put 5 and 5 together, I get 10, and then 100% minus 10% is 90%. So there's the 90% right there. And then I'll do my little computation and I get all the information. Again, lower limit, upper limit is what I really want. So this is about negative 9.3. I'm just going to round to the whole number because it's ages. So about negative 9 years, and this is about negative 5 years. So we have a lower limit of negative 9 and an upper limit of negative 5. So back to my thing here. Wrong one. Back to this one. And for the confidence interval, I do my little readout here. And I have a lower limit of about negative 9. And my upper limit, I think, was negative 5. So we now know, or at least now we have confidence, 90% confidence, that the true difference in average ages is between 5 years and 9 years. The reason why these are negative values is because the actresses are younger. They're somewhere between 5 years younger and 9 years younger than the actors, right? So that's why the negatives are there, because they actually are younger. So we are 90% confident that the actresses are younger than the actors. I guess the actresses' mean age. I gotta put that in there. The mean age are younger than the actors' mean age. Because I'm not just measuring people; I'm measuring their age, right? So the actresses' mean age are younger than the actors' mean age by between 5 and 9 years. Okay, so that is the confidence interval for the matched pair thing. So we're just going to recap real quick what this video has tried to go over. Going back to the original slide here, we are comparing two populations, and we're doing it under 3 different versions. One version is we're looking at the proportions of 2 independent populations, and we're trying to compare those two. The second version is we look at the means of 2 populations that are independent of each other. So we're comparing 2 population means that are independent. And the last version is we're comparing 2 population means, but the populations are not independent. They're definitely connected in a matched pair situation. And we want to, again, be able to compare the means of those 2 populations that are matched up. If you have any questions or would like any more help, have any what if scenarios or any kind of questions, please don't hesitate to reach out and let me know. And I hope you have an enjoyable day, rest of your day or evening, whenever this video finds you. And perhaps I'll see you in the next video. Okay.